Alright, welcome everybody. So today we're going to talk about voltaic cells, and I'm kind of coming at this from an angle that you've already seen these and you have some idea of what they mean. So I'm going to go, somewhat quickly through this because this should be kind of a review to you. So the purpose of a voltaic cell, sometimes called a galvanic cell, is to produce electrical energy. So you have chemical energy, the chemicals, they react, they produce an electric current, you use that electric current to drive electronics. This is your basic battery. So showing you here in the diagram, if I were to circle this, this would be a single cell battery, split into two half cells. The reaction is spontaneous, that means that it occurs without any outside help, that means that the delta G is going to be a negative value. This will do work to the surroundings. Remember back a long time ago I said, yeah, chemistry, we don't do any work. Well, here's a situation where chemistry is being applied and you can actually do work. So this is my electrochemical cell, what I circled in red. It has two parts to it. It has an anode, it has a cathode. So when we look at these half cells here, we can see what's happening. And in this case, you would be given like the overall reaction. And the overall reaction is given at the bottom of the slide here. I'm going to highlight this, something a little bit darker. So you can see there, that's the overall reaction. And we can see that the zinc is being oxidized. So the zinc is turning into Zn+2 ions. What's not shown here is that in this diagram here, we have the zinc basically floating, solid zinc floating in Zn+2 ions. And these are aqueous. The copper is floating in Cu+2 ions. Notice they made it blue for effect. Copper normally is a blue ion when it's in water. And so the zinc is being oxidized. And so that basically means that the zinc solid is turning into zinc aqueous. So our solid zinc is becoming Zn+2. It's being oxidized, so it's losing those electrons. Where are those electrons going? Well, they only have one place to go, and that's through the wire. And this is showing you the wire right here. Now, this is an oxidation, and the oxidation occurs at the anode. Just to be clear, the solid zinc itself, that is what the anode is. Each of these pieces of metal, the zinc and the copper, are electrodes. This zinc is the anode. The copper is the cathode. So let's take a closer look at what's happening with copper. Well, it's being reduced. The Cu+2 ions that are in the solution are actually materializing into solid copper. And this is a reduction. And this reduction, again, occurs at the cathode. A nice fun way to remember this is anox, red cat, like an oxen, and red cat, like, a feline. So anox and red cat. So this is my overall cell. There are parts and things that you need to know about the cell, and we're going to get into them right now. The first thing is you need to know what an anode is. I kind of mentioned to you what an anode is, but just to define it down here, an anode is the solid electrode where oxidation occurs. And the cathode is the electrode where reduction occurs. Now, not shown in the diagram above is a salt bridge because they're actually using a porous barrier here. But whether it's a porous barrier or a salt bridge, the purpose of this is to allow the flow of electrons. Of ions. I said electrons, I apologize. Allow the flow of ions. Now, what ends up happening is, and what you'll see with the salt bridge or with the porous barrier, is that the anions, which are negative ions, they will flow to the anode. And the cations, the positive ions, they will flow to the cathode. Now, just to show you up above here how that would work, I showed this Zn+2 and the Cu+2 here in the half cells. They also contain NO3- as well. So now take a look at what's happening over here the cathode, at the cathode, the Cu plus 2 is becoming Cu solid. We saw that in the half cell over here. Cu plus 2 is becoming Cu solid. That basically means that Cu plus 2, the concentration is decreasing over time. And that's not good for this cell because there will be a buildup of nitrate in that side. So what will happen is if you have this porous barrier or salt bridge, positive ions will be able to flow and take the place of the copper ions. So that's what I mean by positive ions flow to the cathode. The positive ions will replace the copper ions that are being reduced. The same thing at the anode. The anode, the Zn solid, is actually turning into Zn plus 2. And so as that happens, as the Zn turns into Zn plus 2, we get a buildup of Zn plus 2. And so then we'll have negative ions, probably nitrate in this case, coming across the barrier to balance out that Zn plus 2. So it's all about balancing the charges. If we don't balance the charges properly, then we end up in a situation where the cell just won't work. When I build a cell and then I take out the salt bridge, as soon as I take out the salt bridge, the cell voltage goes to 0. Okay, the electrons, so these will flow from anode to cathode through the wire. And so the electrons will always flow from whatever's being oxidized to whatever is being reduced. The electrodes are the solid pieces of metal. In a voltaic cell, the anode is negative, the cathode is positive. And if we think about this, when we look back at the anode, somebody usually says to me, but it's losing electrons, it should be getting more positive. But when you think about what's happening at the zinc, as it loses electrons, those electrons build up in the wire here. And then as they repel each other, they move through the wire. And so the situation is that you sort of have this negative sort of buildup of charge by the anode. Which electrode is increasing in size? Well, we saw that the Cu plus 2 was actually becoming Cu solid. And so the cathode will always increase in size. And the anode, we saw that the zinc was becoming Zn plus 2, and so the anode will always be decreasing in size. Now, something that you'll be required to do is calculate the voltage. And the voltage is what they call a cell potential. And when we look at a volt, it's basically the energy, so 1 joule, to move 1 unit of charge, 1 coulomb. So a volt is a joule per coulomb. And that's going to be the most important unit that we use is the volt. But when we do other types of cells, we're also going to deal with amps. And amps is a current. It is how many charges are passing through the wire per unit time. So that's coulombs per second. Now, when we think about the unit or the charge of an electron is really small. It's like 1.6 times 10 to the negative 19th coulombs. So it's really small. If you take that number and you multiply it by Avogadro's number, 6.02, you get the charge per mole of electrons. And that's what Faraday's constant here is. Faraday's constant, 96,500 coulombs for every mole of electrons. Now we're going to be calculating voltage, and the voltage is considered the standard cell reduction potential that you're given. You have to manipulate that in order to find the cell potential. You'll be given either a mini chart or a larger chart in which you'll have to take the cell potentials and use them. And so one way of looking at this is the cell voltage is equal to the reduction potential of the cathode minus the reduction potential of the anode. And I can look these up. If I look up the standard reduction potentials for these on this table, I would have my copper here. So my copper is at the, where are you, copper? There we are. So there's my copper, and there's my voltage. And my zinc is right here. And so if I do cathode minus anode, what I would have is this. I would have my voltage of the cell that I built before would be the cathode, which was 0.34, minus the anode, negative 0.76. And when I add this together, I would get a positive 1.10. Notice that it's a positive voltage. This also tells us that the reaction is spontaneous. Now, all these voltages, they're based on the standard voltage potential of the hydrogen half cell, in which we have a platinum cathode, and we have the reduction of hydrogen, and we have the oxidation of zinc in this case here. And you can see that in this case we get 0.76, so they measure it against this standard hydrogen half cell. In this diagram they actually show a salt bridge, and again you have the negative anions moving to the anode, the positive cations moving to the cathode, the electrons moving through the wire. Here is a table. Now you're not going to be given this huge table anymore. They cut that out. They give a much smaller table. But the most easily reduced, the strongest oxidizing agents, and I have a slide on oxidizing agents that will talk more about it. But the most easily reduced, those here, since these are all reduction half potentials, they have the most positive values. The ones that are most easily oxidized, they would have the most negative reduction potentials, but they would have the most positive oxidation potentials. Because in reality, what we're doing really is we're flipping this equation around. If we take Al, for example, when Al is oxidized and becomes Al plus 3 electrons, this now becomes positive 1.66. So we'll practice this in class. We'll build some cells and we'll go through how to do them and how it works. Here's the slide on oxidizing agents and reducing agents. The oxidizing agent, it's the substance that's being reduced. So it's oxidizing the other substance, why they call it an oxidizing agent. Reducing agent, that's the substance that's being oxidized, and it's reducing the other substance, that's why it's the reducing agent. Now, like when I look at this, sometimes they ask about the oxidizing agent. Just in your mind, change it to, it is the substance reduced. If they ask you what's the oxidizing agent, they're asking you what's being reduced. If you're spontaneous, like I had mentioned before, the voltage will be greater than 1. And so generally, when we look at this table here, we'll see that the element or the half reaction that's higher up is the one that is more easily reduced. And the one that's lower down with a more negative voltage, that voltage is going to be flipped around as it's oxidized, and that one will be the one that is oxidized. One last thing I want to point out with this chart, based on the chart we can see here the hydrogen half cell. Any of the metals that are below it, in this chart at least, they can be dissolved in acid. So one last thing I just want to introduce to you is free energy. And what I really want to get to with this is the bottom equation right down here, without going through the derivation, that the delta G of the reaction for one of these electrochemical cells is equal to negative NFE. And I tell you that F is Faraday's constant. That's where we're going to use that. N is the moles of electrons. So when we have the moles of electrons, I should write that in here. So N is equal to the moles of electrons. And the E cell is equal to the standard cell potential. This equation, you're given it on the AP exam, so I wouldn't worry about memorizing it too much. Now we can also relate the equilibrium constant to this, and we can relate the equilibrium constant to the cell voltage. With either one of these equations, if you want to do it in log base 10, you could have this, or if you want to keep it in natural log, you could have the equation on the left. So this allows you to relate the cell potential to the standard or the standard cell potential to the equilibrium constant. Now I'm going to stop here. What we can talk about next time is the Nernst equation and cells at equilibrium, and then get into what electrolytic cells look like. All right, thanks so much for watching.